Welcome to DigiKey's live Google Hangout. I'm Anessa Lauer, Product Manager at DigiKey. Today we're hanging out with efficient power conversion, discussing the evolution of semiconductor materials. Currently, it is becoming more difficult to enhance performance of silicon-based MOSFETs. Because of this, customers are looking to other technologies in ways to boost their performance. With us today to discuss one of these technologies is EPC, to discuss their enhancement mode gallium nitride power transistors. Here from EPC, we have CEO Alex Lidow, Executive Director of Application Engineering Michael DeRoy, and Marketing Director Renee Yager. While you are watching EPC's presentation, if you have any questions, please tweet us using hashtag DKHOA, and we will have a short Q&A after the presentation. Now I'll turn this over to EPC.
Hi, Anessa. And hello, everybody out there. I'm Alex Lidow. Renee Yager is to my right, and Michael DeRoy to my left. Let's get started talking about gallium nitride, a pretty exciting new technology in the world of semiconductors. We'll just get started here. All right. And today we're going to start by telling you about the ideal power switch and showing you why gallium nitride is pushing us closer and closer to that ideal. And we'll also talk about when GaN is ready for you in particular. It's ready now for many people. We've been in production for 3 years, and the transition is occurring quickly. And we'll give you some demonstrations of some new applications for our devices and take your questions. We've been in this business for a long time. I started off in the late 70s making power MOSFETs, and throughout all that time, the same questions are asked and the same things are wanted by our customers. And the power switch wish list has not changed probably in 100 years. Everybody wants lower on resistance, because lower on resistance means less conduction losses, less heat generated. Everybody wants devices that are faster. Faster means you get less switching losses, and usually it means that you can make your circuits smaller. Also, less capacitance. Capacitance has to be charged and discharged. That adds power dissipation. It also adds to the amount of energy that you have to supply from your drivers to power the transistors. Folks want things smaller. Smaller is usually cheaper. If you take up less space on your printed circuit board, you can buy less printed circuit board. That's pretty expensive real estate. And then finally, everybody's asking for lower cost. So let's see why gallium nitride materially improves in all these characteristics. In order to do that, we've got to start with why gallium nitride. And I'm going to make a comparison between silicon, gallium nitride, and silicon carbide to show you how these wonderful material properties of gallium nitride actually theoretically create a superior device. There are 3 main physical properties of the crystal that are important to this discussion. The first one is the band gap energy. And I'm showing you for silicon in the center of this chart. And the band gap energy is the energy that binds the atoms together in the crystal. For silicon, it's 1.12. Well, how tightly the atoms are bound in the crystal contributes to something called the breakdown field. That's the second one down. And that tells you how hard it is to break the atoms apart. And that breakdown field in silicon is 0.3. It also tells you how close you can put terminals together in a device before they arc. And then finally you have electron mobility, which tells you how easily electrons float through the crystal. Now let's compare with gallium nitride and silicon carbide. You can see that both gallium nitride and silicon carbide have much wider band gaps. 3 electron volts versus 1. That means the atoms are much more closely tied together in the crystal. And what that means is you have a much higher breakdown electric field. A factor of 10 better for both gallium nitride and silicon carbide. What that means is you can bring your electrical terminals 10 times closer together. And therefore, the resistance between those terminals will be 1/10. So not only have you made your device smaller, but less resistance between the terminals. And in fact, you can pack 10 times more electrons in that small distance. What that means is you get 10 times 10 times 10, or 1,000 times better theoretical performance. Now let's compare the third characteristic, the mobility. And you can see that gallium nitride has the best mobility of all three semiconductor types. And that means the electrons can scoot around with the least amount of resistance. This translates into a graph that we're showing right now, where on the vertical axis, we've put the on resistance of a 1 millimeter square device, the theoretical best on resistance you can get for that device for a given breakdown voltage. And the breakdown voltage is on the horizontal axis. And we've drawn where EPC's gallium nitride EGaN FETs are on this theoretical curve. Silicon, in the upper left, is the least efficient of the three materials. Today, after 35 years of producing power MOSFETs, you can actually buy power MOSFETs right on that theoretical limit. And you can see that EPC is already a factor of 3 to a factor of 10 better than the theoretical limit for silicon with our early generations of enhanced mode gallium nitride field effect transistors. And as the technology improves, we follow that arrow and get closer and closer to the GaN limit. And you can see that gallium nitride is superior to silicon carbide, and that's because of the mobility of the electrons that we saw in the prior slide. So what does this mean? Well, for one thing, it means that EGaN FETs are smaller. And I'm showing you a comparison between an actual silicon device and an equivalent EGaN FET. Now, the EGaN FET is much smaller. If you looked at the silicon device inside this package, the EGaN FET would still be 5 times smaller. But why do I show it compared to a packaged transistor? That's because our EGaN FETs do not require the bulky, cumbersome, and expensive plastic packaging that are required of silicon transistors. So this is a real comparison of how much space it would take on your PC board for equivalent performance. So EGaN FETs are much smaller. EGaN FETs are much faster too. And on this graph, I'm comparing a common figure of merit, or FOM, where you multiply the on resistance of a device times the charge that it takes to apply to the gate to turn it from on to off or off to on. And this RQ product, the smaller it is, the more efficient that device is relative to other products. And here I'm comparing against the state-of-the-art in silicon power MOSFETs. You have Infineon, International Rectifier, Siliconics, and Fairchild devices represented here, and our EPC 2001 100-volt EGaN FET on the far left, and it is 5 times better than the best silicon in the world. That translates into efficiency. And in this chart, I'm showing you the efficiency of a point-of-load converter, one of the most common types of power supplies you can find in this world. On the vertical axis, the efficiency of this point-of-load controller. On the horizontal axis, the output current, and we're comparing MOSFETs against our EGaN FET. Again, we picked the best MOSFETs in the world, and this is 12 volts in, 1.2 volts out, operating at 1 megahertz, switching frequency, and you can see the EGaN FET point-of-load converter is a full 3 to 4 points better than the MOSFET-based converter. This is showing the family of devices. Our second generation of products are listed on the left. They range from 40 volts all the way up to 200 volts, from 4 milliohms all the way up to 100 milliohms. It comes in 5 different die sizes. Just recently, we introduced a middle-sized die size, which I'm highlighting here, the EPC 2016. And you can see the various features of this chip-scale package. These devices have interleaved drain and source electrodes. There's solder bumps, and then there's a gate and a substrate. In this intermediate size, it's 2.1 millimeters by 1.6 millimeters. That's pretty tiny. And that produces a 100-volt device with a 16 milliohm on resistance. Also in the last month, we introduced the 2018 150-volt intermediate voltage device, which I'm highlighting here. Again, interleaved drain and source, gate and substrate electrodes. It's 3.6 by 1.6 millimeters, and it's 25 milliohms. These parts are available today by pushing the Buy Now button on our website or going to Digi and buying it off the shelf there. A few weeks ago, we introduced our third generation of EGAN FETs. These devices are faster and have a better figure of merit than our second generation parts. They range from 40 volts all the way up to 100 volts, and we size them to be much smaller than the second generation part. So you can see the on resistance ranges from 125 all the way up to 500 milliohms, and that's because we're aiming at smaller power level applications such as envelope tracking and wireless power. The capacitances, or charge, the gate charge, gate drain charge, they're all much, much smaller than our second generation devices. And the product of on resistance times charge is also improved. What does this really mean? Well, it means that these devices are fast as can be. Now let's give you an example. And we're going to talk about a buck converter. This is the EPC 9107 demonstration board, which is available today from Digi or through EPC's website. And it uses two of these EPC 2015 EGAN FETs. They're 40 volt FETs. And I'm showing you a switch node waveform from this power supply. And you'll notice that the rise time from this demonstration board is about 1.1 nanoseconds at 15 amps. That is pretty fast, especially when you consider that the driver IC, which is the Texas Instruments LM5113, is switching at 1.2 nanoseconds. So these parts are transitioning faster than their driver IC. Also, you'll notice because of the very efficient layout that there is only a 3 volt overshoot at 15 amps. So we have a 28 volt signal here with 3 volts of overshoot. And that is a product of a very efficient, very tight layout. Here's the efficiency you can get from this demo board. In black, we have 12 volts in. In red, we have 24 volts in. All of them 1.2 volts out, and they're all operating at 1 megahertz, and we're comparing it against the best MOSFETs we can find. As you can see, there's several percentage points difference in efficiency between our EGAN FETs and any MOSFET that you can get out there. Plus, you can go all the way up to 24 volts in the input and 1.2 volts on the output and still get 84–85% efficiency. So, when's the time to convert? When's the time to get rid of those aging power MOSFETs and go with EGAN FETs? Well, over the last 35 years, we've had experience with MOSFETs converting over from old bipolar transistors. And we found that there were 4 main things that controlled the rate of conversion of a new technology in the semiconductor world. First of all, did it enable significant new capabilities? If it did, those were the early adopters. Those were the applications that converted immediately because there was no other way to do it. Secondly, is it easy to use? The easier a new product or new technology is to use, the more likely an engineer can get their first generation or first pass system to work well. The less amount of work it takes, the less amount of time it takes. Therefore, the more likely it is that these devices will be used. Third, is it very cost effective to the user? Because in the end, nobody's going to convert and make their system cost more as a result. And finally, is it reliable? These products aren't reliable enough for the application. There's no reason to convert, no matter how much it costs. So let's take a look at some new capabilities. The EGAN FET, which has been around for about 3 or 4 years, is primarily enabling applications that require high speed. A couple of examples are envelope tracking and wireless power. You'll see a demonstration of wireless power in a minute. And our third generation EGAN FETs are a good illustration of that. On your left-hand side of the chart is an actual waveform of our EPC 8007 driven by an LM5113 driver from Texas Instruments. This is on our new demo board that you can buy from Digi 9027. And the rise and fall times on this are each about a half a nanosecond. So even though the driver IC is putting a gate signal in as a rise and fall time of 1.2 nanoseconds, these parts are switching in half the time of their own input signal. half a nanosecond. This is the first time you can switch this kind of voltage, this kind of power level in sub-nanosecond speeds. And it's a result of the higher gain. On the right-hand side of this chart, you can see the gain curve versus frequency for the 8002, another member of our Generation 3 family. And at 1 gigahertz, we still have 22 dB of gain, 11 dB of gain at 2 gigahertz, and in fact, a little over 7 dB gain at 3 gigahertz. So these parts can be used well into the gigahertz range. They can be used to make switching power supplies well in the tens of megahertz range. Are they easy to use? Well, they're just like a MOSFET. EPC's enhancement mode gallium nitride FETs were designed to look just like a MOSFET. Except, there are a couple of things you have to keep in mind. These parts are very high-frequency parts, and that high-frequency capability makes them more sensitive to circuit layout. EPC has many papers on our website and our demo boards as well that use very, very special layout techniques in order to reduce overshoot, reduce ringing, and make these devices perform with extremely high efficiency. Second thing is that the gate is a little bit more sensitive than on a MOSFET. It has a maximum voltage, 6 volts of the gate. Beyond that, you can damage the device. Therefore, you need to have tight regulation on the gate because it takes about 4.5 volts to turn this part on. The new ICs out in the marketplace, such as the LM5113 or the LM5114 from Texas Instruments, on chip, regulate this gate voltage and make it easy to use. Of course, one of the things that makes these EGAN FETs easiest to use is that they're available right now off the shelf from Digi. Order it now and you can get it tomorrow. Are they cost effective? Well, the answer is that today EGAN FETs are a little bit more expensive than a MOSFET. But let's look at how that goes into the future. And in order to do that, I'm going to compare the cost of a silicon wafer versus an EGAN wafer. Now, silicon MOSFETs and EGAN FETs are all built on wafers. And these wafers go through a wafer fab. And if you build one of these wafers on gallium nitride versus silicon, you can compare the cost by looking at 5 elements. Starting material, growing the epitaxial crystal. In the case of gallium nitride, that's gallium nitride. In the case of silicon, it's silicon. Fabricating it in the wafer fab where you put masks and you etch them and you do all sorts of things there. You test them and you assemble them. When you add it all up, that's the cost comparison that we're looking for. And in 2012, we can look on the chart here and see that the starting material is the same. Well, that makes sense because both our EGAN wafers and silicon wafers start with a silicon wafer. But the epi growth in EGAN, growing this gallium nitride crystal on top of silicon, is more expensive than growing a silicon crystal on top of silicon. The wafer fab costs are the same, and that's because our EGAN process is much simpler than silicon, but we're still running at lower volumes. Testing's the same, and assembly for an EGAN FET is half the cost of a silicon MOSFET. The reason is we don't need a package. And in a silicon MOSFET, packaging is half the cost. So what about the future? Well, we are working with various equipment manufacturers to make a next generation machine for growing gallium nitride epi. And we believe that by 2015, we will have the cost substantially the same as growing silicon epi. At higher volumes, our wafer fab costs will be lower. And overall, in 2015, we believe that EGAN FETs will cost significantly less than a silicon power MOSFET. But are they reliable? And the answer is yes. We have millions and millions of hours of high-stress testing behind us now. This is just showing you a few selected charts. On the upper left, you can see the on resistance after 1,000 hours of burn-in under maximum stress. On the upper right, you can see threshold voltage. Again, after 1,000 hours, you can see on the lower left a power supply, a series of power supplies that will run for 3,000 hours under maximum stress. And on the lower right, you can see our devices, chip scale devices, that were stressed for 1,000 hours with maximum voltage on them and high humidity environment. So even though there's not an encapsulation inside of epoxy, our bare die can last for thousands of hours in even a high humidity environment. So yes, they are reliable. Now let's go to a product demo. I'm going to turn it over here to Michael DeRoy, who's going to show you some new applications for our EGAN FETs.
Hi everyone, thank you Alex. Today I'm going to demonstrate two systems. The first is a wireless transfer technology. It's a very exciting technology that's emerging today, particularly for the cell phone or mobile device charging market. And in this instance, we're going to demonstrate this board here, which is a loosely coupled, it's considered loosely coupled, where the source and the device have some separation between them. And it is operating at 6.78 megahertz, which is the lower ISM frequency band. In this demonstration here, I have a source board, I have a source coil, I have a device board or coil, and a device board. As you can see, I've powered it up, and I have this little hockey puck with an LED in it, and as I bring it closer here, you can see how the light is turned on. As I bring it further away, it has less energy there. This system has a peak efficiency of around 70% using the gallium nitride transistors, and when we build the same system with MOSFETs, equivalent MOSFETs, we're getting around 66% efficiency, and that is giving the gallium nitride version a 4% advantage point. Next, I'll demonstrate the Class D audio system. Here we have a bridge-tied load, a stereo Class D audio system. It is capable of 150 watts into 8 ohm speakers or 250 watts into 4 ohm speakers. The system uses the EPC 2016 devices and the LM5113 gate driver. This system has no heatsink and can operate at full power without a heatsink. I'll turn it on and play some music for you. I'll turn up the volume. Unfortunately, this digital link doesn't do it justice, but we'll talk about why do EGAN FETs offer us a superior Class D audio system. The lower on resistance coupled with the lower output capacitance of these devices offer us higher efficiency and lower distortion of the switching waveform, and that translates into a higher damping factor or a low open loop output impedance. Those are critical factors when looking for total harmonic distortion that is imposed on the audio signal.
All right, well, we want to first apologize for Michael's selection of music. But other than that, we're going to move back and show you a little bit about our products. Just 1 second.
Okay, so you've just heard that the future of semiconductor materials is here today, and you're ready to get started. Well, EPC and Digi make that really easy for you to do with a full line of development boards and demonstration circuits stocked at Digi, so you can get started right away. For every product voltage, we have a half-bridge development board. This is a partial circuit, essentially the power block, that contains the EGAN FETs in a half-bridge configuration with onboard gate drive, dead time control, and the optimal layout. So we've taken care of all the critical components so you can get a really quick, easy evaluation of the switching performance of these FETs. The latest addition to this family is the EPC 9027, which features one of our latest Gen 3 EGAN FETs, the 40-volt EPC 8007. We also have a growing family of full demonstration circuits. These are complete converters, and in most cases are closed loop. The latest addition that we were talking about earlier is the EPC 9107, which is a 28 volt to 3.3 volt buck converter operating at a megahertz and using our optimal layout techniques. Now, we make all of the design files for our board available on our website. So if you go to epc-co.com, this is what the front page of our website looks like. And if you click on to Demo Boards down here in the EPC store, you'll find the full listing of development boards and demo circuits, along with all of their design files available for download. If you click on the Buy Now button today, you can have your board delivered tomorrow from Digi. Okay.
All right, thanks very much. And I think now we're ready to take some questions.
Okay, the first question coming through. What are the key advantages of EPC's enhancement mode transistors compared with power MOSFETs?
Yeah, I think that the biggest advantage that people find is that they are so fast, and that enables new applications. But in addition to being fast, they're very small. And so people have been able to miniaturize their systems, point-of-load converters in half the size. And the size compared with the high speed, they reinforce each other. You can get very small inductors and capacitors because you're operating at higher frequencies. And of course, they're pretty easy to use and they're immediately available.
Okay, we have another question. Does the GaN have a body diode? How does it compare to silicon MOSFETs and forward voltage drop reverse recovery characteristics?
Yes, it does have a body diode, and I'd like to just take a second and show you what it looks like. I think I have a picture here to show you how it operates. Just give me 1 second, and we'll see it. Just takes a second to switch on to this. There we go.
There we go.
So how does the diode work? So this is part of our seminar that we're giving around the world right now, and this is what a cross-section cartoon looks like of our EGAN FETs. On the left you can see a source, on the right you can see a drain, and those little circles with minus signs represent the electrons that are everywhere except underneath the orange gate. Now if you apply a positive voltage on the gate, it will bring the electrons to the surface because opposite charges attract. And that's why we call it enhancement mode. You have to put a voltage on the gate to get the electrons to complete this circuit. Now, if you look at this device from the other direction, you can see that applying a positive voltage from the drain to the gate would do the same thing. Sucks the electrons up. And therefore, it conducts just like a diode in the reverse direction, except the mechanism is different. In a power MOSFET, it actually uses a p-n junction diode. And that's actually pretty inefficient because it has minority carriers. What that means is that you're going to have a reverse recovery time from these minority carriers that have to die away slowly. In our EGAN FETs, we don't have it. And therefore, you have zero QRR, or recovered charge. And one disadvantage is that this diode has a slightly higher forward drop. And I'm showing you the drain source, or the source drain current on the vertical axis compared to the source drain voltage, or the diode drop on the horizontal axis. And you can see for an EGAN FET, it's somewhat higher than for a MOSFET. And therefore, if you're using the diode a lot, the forward drop will give you, it will be more inefficient with an EGAN FET, but you have no reverse recovery charge, and therefore you will gain efficiency from that. In general, it's more efficient to not use the diode in either a MOSFET or an EGAN FET. All right, what kind of questions do we have coming up?
Okay. How do I assemble EPC's enhancement mode GaN transistors?
I think we actually have some good stuff on our website, and I'm going to go to our website and show that to you here in 1 second. Let's take a look at this. So if you go to the front page of our website, you'll see the storefront, and you'll see also our library on the left. And one of the books says Assembly Resources. You click on that book, you'll get to a landing page that has a series of articles and videos that show you not just how to assemble, but how to disassemble this stuff. And of course, they're starring our own Michael DeRoy, and he plays no music in the background, so they're very good. We also have quick reference guides that you can get, which are good for if you're trying to get a technician in your engineering lab to follow a recipe formula. These should give that to you.
I can add to that. For production, we put a lot of information in our data sheets on how to design the pad, and solder mask, and the stencil. So following those guides, most of the manufacturers we've worked with have been very successful at assembling our devices to the boards.
All right, I think we have another question up here, and that's, let's see, paralleling. How about paralleling? Well, the devices do parallel quite well. As a matter of fact, you can go back to our website and you'll find it in the same place under eGaN FET Basics. And if you click on that, you'll get to a landing page for FET Basics, and you have to go into Design Basics, because that's where we are. We're designing, and then you'll find a whole tutorial on how to parallel eGaN FETs. They're actually quite amenable to paralleling, and in fact we have a demo board. What's the number on that?
The EPC 9108.
9017 has
9017 has parallel eGaN FETs in it, so you can actually buy a demo board that has them on it, or read our article, and you'll see how to do it. It's very straightforward.
Okay, there's another question. Can I design my PCB with eGaN FETs with only 2 conductor layers?
I think the answer is yes, you can. We again, under Design Basics, you'll see layout techniques, and it'll show you various ways of doing it. The new devices that we've just come out with, our Generation 3, are particularly laid out to be extremely efficient in a two-layer PC board. In general, we find our engineers want to use more layers for more functions and features, but it can be done with 2.
Okay, we have another question. The high frequency cap of the devices could be an issue with layout of my circuit board. What must I be mindful of laying out my circuit?
Michael.
Yes. Okay.
I'll turn it over to the real expert.
Well, the high frequency cap you got to keep in mind needs to be low equivalent series inductance. That's the first key you want to look at. So in general, the devices that we're working with are very small. So the bus capacitors, the high frequency capacitors, will also be small. And you want to choose capacitors that have got a low profile that will also keep the inductance down. And then on top of that, if you follow our guidelines for the optimal layout, it will also help you to keep the inductance in the loop low. And lastly, if you place additional capacitors, you spread them out width-wise, you can make a wide conductor trace and a shorter conductor path, and that will also help keep the inductance low, making your layout a good layout.
And as I said, we make the design files available for our boards, so the EPC 9017 and the EPC 9107 both have the optimal layout included on those boards, so you can take the Gerber files right from our site and use that layout.
Okay, we have one more question.
There's another question about testing. Nissa, let me just take this one. It's the question is, how do we test these things? And you know, eGaN transistors are not that difficult. They're like a MOSFET. but we do offer a tutorial on that, and I'll click over to that in a second here. And again, it's available through our website. You go to our home page, you go to Basics, and then you go into Design Basics, and you will find all sorts of information, including this thing called EGAN Parametric Characterization Guide, which gives you a step-by-step methodology for testing each and every one of the datasheet parameters.
Okay, I don't see any other questions at this time.
All right.
All right, well, if there's no other questions, I want to thank EPC for hanging out with us today.
Thank you.
All right, thanks very much.
Okay, and thank you all for joining us.